children.
About the periodic table. Pretty much everyone knows what this is, even if they don't know much about chemistry. It's the periodic table of the elements, which at first seems like a random arrangement of substances, most of which sound strange in form. But the way the elements are arranged reveals many beautiful patterns that tell us about how nature operates. In the mid-1800s, lots of chemists were trying to come up with a way to depict all the elements in table form, and many different formats were proposed. But it was the one by Dmitri Mendeleev that stuck, because of how well it correlates data, as well as its predictive powers. He arranged the elements into rows called periods, and columns called groups. Elements that had similar behavior were put in groups together, which helped to correlate existing data. It also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in these spots, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected, and now we have all the metals, metalloids, and non-metals organized nicely. It wasn't known at the time, but the reason elements in the same group behave similarly is because they have the same number of valence electrons. Look at group 1, for example. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and n increases, you gain a shell each time, but whichever is the outermost shell, there is only one electron in it. Every element in group 2 has 2 electrons in its outermost shell, and so forth. This simple fact determines many characteristics about each element in ways we will continue to see as we learn more chemistry. There are some periodic trends that we can recognize when we look at the table. The first one is atomic radius, or the size of the atom. As we proceed downwards on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell, and each element to the right has one more proton in the nucleus than the last. So there is a stronger electromagnetic attraction felt by the electrons, and the radius shrinks. That means overall, atomic radius increases going this way on the periodic table. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away makes it smaller. Ions with the same electron configuration will have their radii decrease as the atomic number increases. Next, we look at ionization energy. This is the energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electrons to the protons drops off very quickly with distance. So the farther away an electron is from the nucleus, the easier it is to pull it away. This means the ionization energy trend is precisely the opposite of the atomic radius trend. Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus, and atoms like to have their outermost shell completely full. Losing the electron means this shell is gone, and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus, and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium. So the ionization energy increases going this way on the periodic table. Elements can have successive ionization energies for removing more than one electron. A second ionization energy will always be greater than the first and continue to increase from there, since the more electrons you remove, the less stable the atom becomes. An element will have a huge jump in ionization energy after you take the last one in a shell, because then you jump to the noble gas electron configuration from the previous shell, which is full, so it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look, for example, at the second row. From lithium to neon, the ionization energy should increase each time we add a proton to the nucleus and the radius contracts a little. But something like oxygen, which dips downwards from nitrogen's ionization energy, does so because of orbital symmetry. Here is nitrogen's orbital diagram, as well as oxygen's. Notice that nitrogen's 2p orbitals are precisely half full. This gives nitrogen a special stability, just like elements that have a full outermost shell. If nitrogen loses an electron, it loses that special stability. But if oxygen loses an electron, it will gain that special stability. That's why oxygen's ionization energy is a little bit lower than nitrogen's, even though oxygen has one additional proton. All deviations from the ionization energy trend can be explained by discrepancies in orbital symmetry, like this one. Next, we will look at electron affinity. This is exactly the opposite of ionization energy, since ionization energy is how much energy you need to remove an electron, and electron affinity tells us how much an atom wants to gain an electron. Disregarding the noble gases, as their shells are full, electron affinity increases this way. Fluorine has the highest electron affinity because if it gains one electron, it will have a full shell, or a noble gas electron configuration. Looking at the opposite corner, these elements don't want to gain electrons. They would rather lose them. Exceptions to this trend happen for exactly the same reasons as the exceptions to the ionization energy trend. Lastly, we want to look at electronegativity. This is the ability of an atom to hold electrons tightly. It will increase this way because a smaller atom like fluorine with more protons for its energy level, or a higher effective nuclear charge, will hold electrons best. Again, we will disregard the noble gases for this trend. Electronegativity will be important in the next clip where we learn about chemical bonds. So the trends to remember are atomic radius, which goes this way, as well as ionization energy, electron affinity, and electronegativity, which all go this way. Let's check comprehension.
Music's really something.
Thanks for watching, guys. Subscribe to my channel for more tutorials. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right. Well, let's go ahead and get started, okay? All right. So we're going to begin by looking at electronic structure of atoms. So we've got these numbers, right? These quantum numbers, right? What's the N number? What are our numbers? Give me the four numbers. What are they?
N,
N. What else?
L,
L.
and L and S.
What is that?
The big M with the lower L,
Okay.
and N with S.
Okay. All right. So what is my N number?
Principal quantum.
Say it again. Principal quantum number. Okay. And what does that tell me?
The energy level.
Yeah, principal quantum number. Energy level. Okay. And L?
Angular momentum.
Angular momentum. What are these basically?
Shape of some shells.
Okay. What's next?
Magnetic quantum number.
Okay. What does that tell me?
The orientation in space.
Magnetic quantum number. So this is the 3D aspect of it. And then MS is
Spin quantum.
spin. Magnetic spin number, right? So this has two values. It's either just up or down. Good.
Is that M1 or ML?
ML. I think some people probably do it like that. It's easier to see than my L's that look like my ones that look like a bunch of other stuff that I do. Okay. So what do we need to know coming out of this? We want to look at orbital energies and atomic structures. The textbook says the energy of atomic orbitals increases as the principal quantum number increases. So in other words, as I go from n equals 1 to, actually let me do it this opposite way. I'm going to start with n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. As I do this, the energy of these electrons increases. Okay, that makes sense. Lowest energy electrons are in that first orbital. Highest energy are out here in this fifth orbital or beyond. Okay. In any atom with 2 or more electrons, the repulsion between the electrons makes energies of subshells with different values of L differ, so that energy levels of orbitals increase within a shell in the following order: S, P, D, and F. So these are our N numbers, right? Let's do our L numbers. So our L numbers, the lowest energy is S. And the next is P, and the next is D, and the next is F. Okay? And again, this is the energy of electrons. Right. Figure we're going to look at. The map depicts how these two trends in increasing energy relate. Right. So far so good. I'm going to erase this and I'm going to work over here. So what's my, based on these two things, when you think about this, what's my absolute lowest energy level?
M1.
N equals 1, and what shape?
S.
S. So my lowest energy level is going to be my 1s. Okay. My next lowest energy level, what should it be?
2S.
2s. So remember, the first one only holds s. That's it. They don't have any others, right? So we're done here. For the second energy level, what can I hold? S and P. But S is lower energy than P is. So we go 1s, and then the next one is 2s. Okay? And the next energy level is going to be 2p. Okay? Now, that takes care of my n equals 2. I want to go to n equals 3. What's my lowest energy level?
3S.
3s. And then
3P.
3p. Okay? And then
3D.
we think of 3D, which would be like over here, right? There is a weird thing that happens. Okay? Before we start filling 3D, it's actually, it requires lower energy to fill the 4s. 4s happens just before 3D does. You might be thinking to yourself, why? Why does that happen? So, start with the nucleus, my first 2 electrons, right? What happens to my next electron?
So the second
Yeah, it gets pushed out, right? Why?
because it's defeated.
Electron repulsion. There's not enough room, and these electrons don't like to be near each other, so they repel each other. So my next electron gets pumped out, right? Of course, I know that this one kind of looks something like this, right? So it's 3D, I got something like this, I got another something like this, right? It's not good, but hey, it's all right. All right. And of course, it also has an S shell, right? There's my 8 electrons, right? So that takes me through 1s, 2s, 2p. Now I'm ready to go to 3s. 3s is going to be a whole other mess of this, right? I'm going to start with 2 electrons here. And now I'm going to go it's getting to be a hot mess. And we're starting to fill a lot of this space. I've already got, right now, 8 electrons in this space, right? And I'm about to add the 9th, and then the 10th, and actually, with my d orbitals, think about this. How many electrons does this hold? 2. How many does this hold? 6. How many does this hold? What does this hold? 14. Okay. So, at this point, I've got 8. I've got 2 in this s orbital. I got 6 in this p. And what I'm telling you is it actually requires less energy to kick another electron or 2 out here than it does to try to fit them in here. This again comes down to electron exclusion. Right? They don't like being near each other because of the same charge. And so there's enough repulsion from these 8 electrons that it will kick another electron out here, and it'll kick another electron out here. But now these have repulsion, right? And it takes energy to be out here. And they're further away. But there's less energy in them flying further away because of the repulsion from that than there is to cram more electrons in here. But now once these are out here, these do have repulsion, right? And they're out there. And so the next 10 will get packed into this space, right? 10 more. And I can't draw those orbitals in space. I mean, I can barely do that, and that looks like a train wreck. I sure can't do the d orbitals. So the point is, 1s, 2s, 2p, 3s, 3p, 4s, 3d. This is the surprise. Because of electron repulsion, it actually requires less energy to fill the 4s than it does the 3d. Okay? Not the 4p, just the 4s. Let me read to you exactly what this says about that. The 3d orbital is higher in energy than the 4s orbital. That's all it has to say. Okay, electron 6 says it. That's all it's going to tell me? That's all it's going to tell me. Okay. Does this make sense right now? Okay, good. I'm going to erase this hot mess, and we're going to keep going. So what's going to be next? I got 4s, what's next? And then 3d, what's next? 4p. And now what do you expect?
4D.
4d, but what's going to happen before I get to 4d?
5S.
5s. Now I can come over here and I can do 4d. I did not leave myself enough room. Not even close. I didn't pack these tight enough. You've got a really good drawing in your book. I'll go make you all a copy of this in just a second.
You don't have a 4F?
Oh, it's coming.
Is that for me?
So I just got to 4D right here, right? Okay. And now I'm going to go 4F. That's my next one. Okay. And then after 4F is going to come.
5B.
Oh, I'm sorry. I put this in the wrong place. I skipped. Let me make you guys a copy of this. I'm running out of space. I'll be right back. I need 4 copies. We'll have it. Okay, so this shows you this in a graphical form more accurately, better space than I'm able to do, and in proportion. Lowest energy levels are the 1s, followed by the 2s, the 2p, the 3s, the 3p, the 4s. Then we jump to 3d, then we can fill the 5p, then over to 5s, then 4d, then 5p, 6s, then 4f, then 5D, 6P, 7S, then 5F, then 6D. Clear as mud, right? All right. What are we going to do with this knowledge? Well, first of all, let's think about how to think about any set of electrons. Get your periodic tables out. Atomic number 1, what is it? Hydrogen. How many protons does it have? 1. How many electrons does it have? 1. Where's that electron?
First.
What's the N number?
S.
1. And what shape is it? S. And how many electrons does it have in the S? 1. So the valence electron here is going to be 1s1. How do they want this written? I need to make sure I write it the way they want it. Big. Okay. It's going to be this way. 1s1. Okay, so 1s, principal quantum number, L, angular momentum, and 1 letting me know, okay, I've got that. If I want to do helium, right? Helium's going to be what?
2.
Nah. How many electrons, how many protons? 2. How many electrons? 2. How many does the first quantum number hold? 2. So this is going to be 1, S, 2. Okay? Tell me that for helium, I've got 2 electrons in the 1s orbital. Okay? Let's do lithium. How many electrons? Huh?
3,
3. How many in the first?
2,
2. So I'm going to get 1, S2. And now what do I do with my third one?
go to the next one.
Next one, which is going to be 2, S1. Okay. Next up is beryllium, right? So beryllium is going to be 1s2, and then what?
2s2.
2s2. All right. Hydrogen, helium, lithium, beryllium, boron. What do I got? I got 5. Where do they go?
1s2.
1s2,
2s2.
1s2, 2s2, and then what?
3s1.
Nah.
2
2p1. Let's draw it. So it's going to have, here's boron. I got 2 electrons in my first. We know it's an S shape, spherical shape. Then I got 2 electrons in the second, right? In the S, also spherical shape. That spherical shape only holds 2. I got 1 more electron. It's got to go in one of the P shapes. It's got to go into one of these that does this deal, right? So it goes there. So graphically, I've drawn the same thing I have here in a chart form. 1s2, 2s2, 2p1. Okay. And now that's boron, and now next is what, nitrogen? No, is it nitrogen? No, it's 1, 2, carbon. Okay. We'll do nitrogen after that, and then oxygen, and then we'll do fluorine, and then we'll do neon. Okay? And then we'll go skip and do some other fun things. Okay. Carbon. It's got 6, right? Where do they go?
1s2.
1s2,
2s2.
2s2, and then 2p2. Right? 2 in the S, no, 2 in the next S, and then 2 in the next P. Okay. And nitrogen. It's going to be 1s2, 2s2, and then 2p3. This is going to keep going, right? Until we fill these P's. So we'll keep going here. So we're going to go 1s2, 2s2, 2p4. And now 1s2, 2s2, 2p5. And then neon, 1s2, 2s2, 2p6. And then after that comes sodium, right? Sodium has 13. So we change, because we just do that and I'll let y'all catch up.
So will the P's fill up all the way to 8?
6.
6.
Yeah. So there's 8 in the second shell total, 2 in the S, 6 in the P. Once those P's, and just remember, the thing about this is you always put 2 in the S's before you fill any of the P's. And you always fill all the P's before you move on to anything else. So, oh, sorry. Catch up. Okay, sodium. Give it to me.
1s2.
Okay.
Oh, wait, reading the whole thing.
Yeah.
2s2,
Okay.
2p4,
Yeah.
Six.
Good. And now?
Is it 3?
Yeah.
S.
Yeah.
Wait, 6. 3.
No, we only added one more electron. Remember, we're moving up,
So
right?
1. Yeah. so
There we go.
yes.
That's it. Good. That's great. Good, good, good. This makes sense so far, right? Good. I'm going to skip something. Yeah, let's do this. There's another way to represent these, okay? And it's accounting the draw just an S here. Right here. Okay. So these boxes, this is another way of representing this. You've got to be able to do all of this. Okay. Hydrogen has one electron, right? Remember, I've been showing you this idea when we got to that last quantum number, m sub s, the spin number. We can say mathematically it's +1/2, -1/2, but I also said we can draw them up or down because they either spin up or down. So let's go ahead and do that. So this gets an arrow drawn this way. Helium has two. The first one goes this way, and the second one goes this way. Okay? Yeah, you got to do this. Do it with me. Come on. Lithium. I'll let y'all catch up, and then we'll go forward with lithium. There's nothing for this but to do it. There's a reason I'm taking the time to draw. I mean, this is tedious to draw all these out, right? But the repetition will get it in. Like right now, I feel pretty confident that if I said, hey, what's the electron configuration of oxygen with your eyes closed, close your eyes. Close your eyes. Oxygen. Electron configuration. 1, S, 2, 2, S, 2, 2, P, 4. Atta girl. Y'all got it. That's right. That's right. So, but that comes with practice, right? So you got to stay with me. You just got to do this so that when it counts, you can just do it. All right. So hydrogen has 1 spin up. Helium has 2, 1 spin up, 1 spin down. Lithium has
1,
3. All right. First electron,
No.
spin up. Second electron,
No.
spin down. What do I do with my third electron? It can't go here. Right? This is because this is my 1s, right?
You need to draw another
So I gotta start getting some 2s. Okay, so now I need another box. Okay, so now you know what to do, right? We go spin up. And you can do beryllium.
So it's just alternating between both?
Well, it's going to change here in a second. So let's do boron. The boron has 5, right? So the first one, 1s2, 2s2, 2p1. So I've got to draw some p orbitals here. How many suborbitals are there in p? 3. So spin up, spin down, spin up, spin down. The next one, spin up. Done. And now I know that you can finish these, right? Yeah. You guys are pretty sharp. So carbon, 1s2, 2s2, 2p, say 2. 2. Spin up or spin down? Spin up. And the next one? Spin up. Yeah, it's going to... See, this is where Pauli's exclusion principle comes in. Take a look. Stop. Stop. Okay. This one only holds 2. And then we jump in energy level. And this one only holds 2. And we don't jump in energy level, but we do change our shell type and shape. And now we're into this angular stuff, right? And now, in each of these p orbitals, I have 3 p orbitals. One's oriented this way, one's oriented this way, and the other one's oriented that way. And if I had a third arm, I could make that axis, and that'd be really cool. But I don't. So, but the thing is, you fill one of these in each of the p's before you double any of the p's, right? So this one's going to go like this. And now, finally, when I get to this next one, I go up, 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 and then I can put my down. Did you catch that? Every one of these suborbitals gets a spin up before any of them get a spin down. Probably a better way to say that than the way that I said it, but you know, you're stuck with me. So. So fill that out. Like I say, there's nothing for this but to do it. You just got to do it. Do you know what sodium is going to look like?
Oh, I think so.
Okay, what sodium looks like?
It's gonna be up, down.
Well, tell me boxes first of all.
4 boxes.
Okay, so one like this, another like this,
One with 3,
and one with 3, and then
1 again.
one with 1. Okay, so I go
Up,
up,
down,
down,
up,
up,
down,
down,
up,
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 down,
down, down, down, and now
up.
up. Right? And that should give me 13 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11 electrons. It was odd. I had the wrong number with log ones. Okay. Now, there are other ways of doing this. This is only atomic number 11. How many things are on your periodic table? What's the highest element you have? 118. You want to do this for 118? Yeah, me neither. That'd be so tedious. Let's do sodium again. Let's do sodium super simple. Okay? So one of the things you can do with sodium is you can go Isn't that easy? What did I do?
Just show that everything's fuel at 2s1.
Hey, what did I draw here? What is that? It's neon. Where's neon in relation to sodium? Just before it, right? What do you know about neon? Look at it on the periodic table.
10 electrons.
It's 10 electrons.
Noble gas.
It's a noble gas, which means its valence shell is full, which means anything after it's working on a new valence shell. So when I have sodium and I draw it like this, I know, hey, it's the same as, it's got everything that neon's got. 1s2, 2s2, 2p6, full valence shell, plus it's got this extra 3s1 electron, okay? So basically, I'm going, hey, whatever was true down here is also true here and this. And so this is a shorthand way of representing any of these is to give the noble gas that precedes it and then whatever's extra. So sodium becomes neon with a 3s1. I could do the same thing over here, right? I could go, hey, it's neon with 3s with 1s. Right? That's easy. That's convenient. Let's do, I don't know, let's do something else, something slightly harder. Why don't we do chlorine? How many electrons does chlorine have? It's atomic number. 17. Okay. So, I can write all that out, right? But I don't want to do that. I just learned this trick. So what's the preceding noble gas? It's neon. So I go neon. And then, what do I do for chlorine? How many valence electrons does it have? 7. Good. They go here, right? 3s1.
S2.
Or sorry, 3s2. And then
3D.
3p.
3P.
3p what?
5.
5. Right, so there's my 7 valence electrons. If I want to do it over here, I go neon. And then I go, good. Good. Let's do calcium. What's the preceding noble gas?
Argon.
Argon. So calcium, I'm going to do argon. And now? Where's that on your periodic table? 4.
No, 2.
S2. Okay, 4s2. And it means it's got everything argon's got, plus, right? And now, I go here, and I can go, all right, I've got argon, and I've got a 1 box for my 4s, right? And I need to put 2 in it, spin up, spin down, I'm done. Okay. Let's do iron. What's my atomic number on iron? 26. What's its preceding noble gas?
Argon.
It's argon. Good. What does it have beyond argon?
He has like 6 electrons.
It's got 4s, right?
S2.
4s2, and then where do I put them after that?
3D.
3d. This is that weird thing where it takes less energy to fill your 4s than it does your 3d. So I go 4s2, and now I go 3d, and how many does it have in the 3d?
4.
4. I'm having to trust you on that. I don't have that one memorized where it's at. All right.
It's 6.
It's 6.
6.
Really 6.
Okay, good. Good catch. Okay, so if I were to draw it over here, I go argon. And then I need to do my 4s. Right, spin up, spin down. And now I need to do my d's. Well, how many do these hold?
8. 10.
Which is it?
10.
They hold 10, so I've got 5 boxes, right? So 1, 2. That's too many, I'll erase 1, okay. So, I go, how do I do this? I'm putting 6 in them, right? So what do I do?
All
All of them with 1, right? All of them spin up. And then one of them spin down. Good, good. Okay, let's do, bromine. How many atomic numbers, or what's the atomic number on bromine?
35.
How many?
35.
35, that's a lot. We're getting up there, right? What's its previous noble gas?
Argon.
Argon. All right, what do I have that argon does not? Take a look at what iron, where iron was, right? We got 4s, what? 2. Well, I guess what you better do is you better count how many more electrons it has than argon, and then we can figure it out. So count how many more electrons it has beyond argon. 17. It's argon plus 17 electrons. 2 in these s's. How many go in the d's? 10. So that's got to be 3d 10, right? Well, where do I go after my 3d?
4p.
4p. You guys said it had 17 electrons?
Yeah.
Okay, so I accounted for 12 of them, so that means I got a 5 here, right? Perfect. Okay, so that takes care of that, and over here, I got to go argon with a 4s, with a 3d, and with a 4p. Right, this is going to be filled. And then how many boxes are in this box?
3.
3 of them. Good, because P has 3 subs for the spatial orientations. And I need to put 5 in it, so I go up, 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 down, down. If I add one more, what element do I have? Huh?
Krypton.
Krypton, which is a
Noble gas.
noble gas, and now I'll start referencing everything from krypton, right? Good, 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 good. Y'all are doing great. What time is it? All right. Okay, let's see here. Let's look at your periodic table for a minute. I'm going to erase some of this. consider a periodic table here. What are these? What shape are these in terms of valence electrons? These are S. What are these? Yeah, let's go over here. What are these? P. And helium. Helium, in some ways it belongs over here, in some ways it doesn't. We'll talk about that in a minute. So this is our P's. What are these? D's. And that weirdo section you have at the bottom, right? What's that? F. This will often get referred to as the D block. This will get referred to as the F block. If this is S, how many columns do I need to have here? 2. If that's P, how many columns? How many fit in the P's? 6. Count them. How many are there? 6. How many should there be here? 10. How many should there be here? 14. How many are there? 14. So without knowing all of this, Mendeleev and others came up with, like they discovered the effects in repeating periodic trends, the effects that orbital filling had. Just kind of crazy cool. And we've arranged it in such a way that you can see, like, oh, 1s1, 1s2, 1s1, 1s. I'm going to just do the valence, okay? 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. What do I have? 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Right? And then we go what? 4s1, 4s2, then 3d1, 3d2, 3d3. You can actually see the orbital filling on the periodic table, which is cool. Right? All right. You need some off-bow principle. Off-bow is a German word. How could it be anything else? It's not the prettiest language. It's a very aggressive language. It's like somebody's going to hawk a loot on you at any time. You guys ever seen that where they have like somebody say something in like English and in French and then in German? In German, it's always like they're yelling at you. I feel like that's a very American video. Like people in other countries wouldn't do that. All right. Off-bow principle. To determine the electron configuration for any particular atom, we can build the structures in order of the atomic numbers, beginning with hydrogen and continuing across the periods of the periodic table. We add one proton at a time to the nucleus and one electron to the proper subshell until we have described the electron configuration of all the elements. This procedure is called the off-bow principle, from the German word Aufbau, which means to build up. Each added electron occupies the subshell of lowest energy available in the order demonstrated, which you don't have, we'll do it in a minute. Subject to the limitations imposed by the following quantum numbers according to the Pauli exclusion principle. The electrons enter higher energy subshells only after lower energy subshells have been filled to capacity. What we're about to draw illustrates the traditional way to remember the filling order for atomic orbitals. Since the arrangement of the periodic table is based on the electron configurations, this figure provides an alternative method for determining the electron configuration. Filling order simply begins at hydrogen and includes each subshell as you proceed. Okay, what's the first shell I'm going to fill? 1s, right? 1s2. Well, I guess just 1s. And the next one? 2s. Okay. And the next one? 2p. And the next one? 3s. And the next one? 3p. Okay, and the next one? 4s. And the next one? 3d. Okay. And the next one? 4p. Okay, and the next one?
5s.
Should be 5s. Okay, and the next one? 4D. Do we not have D yet? We don't have D yet. 4D is going to go here. Okay, and the next one?
5p.
5p. Okay, and the next one? 6s. And the next one?
4s.
4D, 4p, 6s. 4f, we're right about that. And then 5d. And then 6p. Start to see a pattern. And then 7s. And then 5f. And then 6d. And then 7p. Okay. So this shape is important. The shape of how we've drawn these. Okay. So the S's are all in order. The P's are all in order. The D's are all in order. The F's are all in order. Notice that there's like a stepwise progression, right? 1S, and then 2S, 2P. And then we fill, and then okay, right? And then, right, it goes like that. And the opposite also looks to hold true here, right? There's like a step thing that I see, and okay, we would have one here, but we don't have that. But if you had those elements, then we have that, right? Okay, so this is the shape of this. I can look at this and I go, okay, great. Now, here's what's cool. This will show me the order they're filled in. Okay, I can determine that from this perfectly. This I can just go 1s, 2s, 2p, 3s, 3s, 3p, 3d, 4s, like that's just, okay. Now, I fill them like, I'm gonna use a different color. Because colors are cool and I have some. So I go like this. Fill that first, then I fill this, then I fill here, then I fill here, then I fill here, and here, here, and here. So when I look at it like this, this shows me the exact order that these things fill in. What's my first one?
1s.
1s, and then
2s.
2s, and then
2p.
2p, and then
3s.
3s, then what?
3p.
3p, call them out.
4s. 3d.
Louder.
4p. 5s. 4d. 5p. 6s.
Okay. 4d, 5p, 6s, 4f, 5d. I'm out of energy on this, but you get it, right? So if you can draw this, and you can remember that we're just coming down these hash marks, that'll tell me the order they fell in. Right? I think that's helpful. I think that's really helpful, and you'll probably, I'd expect to have to know that. Okay. practice drawing this? Everybody feels good? Okay, great, perfect. You're better than me. I've been like, yeah, let's draw that. What else? What else? What time do we have? Time to practice problems? Kind of, sort of, do. What is the electron configuration in the orbital diagram for a phosphorus atom? Okay, let's do phosphorus. I'm going to erase. Can I erase this? Erase this. Use periodic table. I'd have mine, anyways, if I were you. What's the symbol for phosphorus?
P.
Huh?
P.
P? It's my atomic number.
15.
15, that's not bad. We can do that. So P, 15, so I got 15 electrons. So, what's it asking for? It's asking for the electron configuration and the electron orbital diagram. So, it's got to fill up, right? So, you guys can do this. What is it? 1s.
Can we do like that?
Yeah.
Neon?
Yeah, this is all it's asking for. Well, humor me on this one. Do it in full for this one. 1s,
2.
2,
2.
2s,
2.
2, 2p,
6.
6,
3s.
3s,
2.
2, and 3p, right?
3.
Okay. Or the other way, as you mentioned, is to go neon, which is 10, right? And then to go, what, 3s2, 3p3. Okay, good. When I want to do this chart, well, I know it's like this, and I know it's like this, and I know it's like this. And then I got to go to my 3. Oh, by the way, I want to label these, right? So 1s, 2s, 2p, 3s, 3p. So this fills up, that fills up, and then I go here. Okay? Okay? Now it's asking you to tell me what element or what atom this is. Okay?
The first one is nickel.
I haven't looked. Is that argon plus 8? Somewhere in the middle of the D block?
It's iron. It's iron.
Okay.
I got the wrong thing.
You guys get iron for A? Good. P. Number of ways I could look at this. Okay, I could go, okay, this is krypton plus 18, and I could just look for whatever that is. I could go, hey, this is krypton with 5s2. I know I'm done with the far left. The D is filled. I know I'm done with the D block, and now I go to the P block, and I'm looking for the 6-1. The 6-1 on the P block is going to be a noble gas, right?
Yeah. Signal.
So this is xenon.
But it doesn't work the same way for D, the D block,
Help me
or
out.
that count. So like, I did for the argon one, the top one.
Yeah.
A,
Yeah.
I basically did that. I just did like D6.
Yeah, so you go down to that D block
And count.
and count 6 over.
Yeah,
What'd you get?
oh, I missed iron.
Okay.
I just missed one of the
Okay. And but here's one thing to think about is there's a good check here, right? Because I know it's going to be the 6-1 in the D block, but I also know it's going to be whatever atomic number argon is, it's going to be argon plus 8. So if those two things don't agree, I've done something wrong. And that, how long does that take? It's a second, right? That's worth taking that second so you don't miss a problem. Okay. I bet we're done. Yeah, it's right on time. Okay. Well, we've got just a hair more to do with this next time, but the rest of it's going to be very easy. This was the hard stuff. Okay. All right. You want to see me?
I think I figured it out. I'll be all right.
All right. So test next class. None of this is on it, right? This will be on the last test prior to the final. You're doing great. Write everything out, right? Write everything out. If you have a question, email. I get them. Right? So I'm here for you.
I've got a quick question about that.
Yeah. What's that?
So I was looking at some of the revision questions that you said.
Okay.
I was
Yeah.
going over them, and the ones where it says, for example, you have a volume of whatever M solution of sodium hydroxide,
Okay.
and then they would just give you, like, without giving you the balanced equation, how am I supposed to figure out the balanced equation just from being given that?
I just have to look at that problem. Can we do that?
Yeah, got everything.
Okay, good.
So I can do the rest, but the balance equation part is getting, like, I can do them for some of them, but when it doesn't give me like a specific, like,
Yeah,
you
here.
know, yes, something like that.
Volume, 8.3 molar solution of sodium hydroxide.
But the question, I don't think he gave you this one.
Okay.
So what happened?
You, in this case, you're going to look up what the formula for oxalic acid is. On a test, I'm going to give it to you.
Okay, okay. All right.
I would never do that to you.
Yeah.